Okay, so what I want to do today is talk about the first course in computing. I understand you guys are reassessing the undergraduate curriculum, and so it's appropriate to get all points of view. I teach the freshman course at UT. I started this freshman course at Michigan, and I'll get into why all that happened. I've actually combined two lectures into one because I don't know how broadly you're evaluating the undergraduate curriculum here, whether it's just the computer science, computer engineering curriculum, or whether it's the curriculum for the whole college. I hope it's a curriculum for the whole college, because if it is, then this first course should really be with perhaps minor modification for the non-computer engineering students, should be the first course for all engineers. So I have a few slides I want to first talk about for all engineering, why this makes sense, and then I will go into a lot of the nitty-gritty of why it makes sense in computer engineering, computer science, electrical in the same way that it makes sense for civils, mechanicals, and chemicals, etc. So here's the compile time outline. I can't give you the runtime outline because we haven't had the talk yet. And runtime is based on things that happen in real time as progress is made, and I have no idea what that is before the talk starts, so I'm giving you the compile time outline, the static schedule that I came up with before I stepped up here today to talk. Why for all engineering students, and then what we do in the first course. I don't know whether I'm going to talk about the ISA or not. It depends on where I am when I get to that. Then some observations, and then some more observations, and then some more observations, etc. First of all, with respect to non-computer engineers, why would you want, to study the bowels of the computer? So at Michigan, where I started this thing, because we were upset with how little the students actually understood with a program in this silly thing called Java. Silly because they don't understand what the computer is doing, and so they are forced to memorize patterns, hoping that when they see the exam, the pattern they memorize will fit the problem they're being asked to solve. Memorizing isn't learning. In fact, if I have any mantra at all, it's memorizing should be thrown out, replaced by understanding, and we'll get more into that as I move along. So at Michigan, I'm a mechanical engineering professor. I want my students to take your course. Why? And they can get away with taking a Fortran course, which was the course that mechanicals and civils, everybody other than EECS students took. Michigan has computer science, electrical engineering, one big department, electrical engineering and computer science. It was a forced marriage that the provost did many years ago, taking computer science from the liberal arts college and moving the degree into the engineering college, and so students would be in all one big department. Even though the degree was still, the degree itself was still offered by liberal arts, but the faculty and everything was in engineering. So mechanicals didn't take this course normally, they took a Fortran course. I want my students to take your course. I can teach them friction, vibration, those kinds of things. But what about the 55 microprocessors that are in the car? And if they don't understand that in the automobile there are sensors, pick up input information, and a stored program that processes that information, and actuators which then do something as a result, then they're going to be a mechanical engineer that's ready for the last century rather than this century. I rented a car. I do not own an automobile. I rented a car in Austin to come here. They wanted to give me an SUV. I don't drive SUVs for lots of reasons, which I shouldn't, get into. Digress to talk that way today. So they ended up giving me a small Lincoln, which is a fancy American car, and I'm amazed at all the computer control that's in that Lincoln. You have to practically do nothing. Everything does it for itself. It's all these microprocessors. one Mickey Mouse example. Sensors that tell you that there's some car passing you on the left, so you don't drive into him or her. And then a stored program that takes that information and you get a yellow light that goes on in your rear view mirror telling you don't move to the left, because if you do, you're going to cause an accident. Just one simple, small example. Students I talked to in my freshman course at the University of Texas, Intro to Computing. Every other year I teach it, 400 students. Most of them, well, this is Texas, so both you and I get the top 10%, This isn't Mississippi here, this is Texas, And they've all had this AP, Advanced Placement 5, from taking Java. And they're completely clueless. They have no idea what's going on. And at the end of the semester, they come up to me, I got to shake your hand, Dr. Patt, because you taught me, now I understand what's going on. And I went through this stuff in high school and I understood nothing. In fact, I would say, by the way, that this freshman course of ours could actually be the senior year in high school. It could be a remedial course in college. It isn't. At many universities, it's taught, the material is taught in the junior year. Teach it in the freshman year, and you provide a solid foundation on which everybody can build. Okay, so what a computer is to an engineer, in particular a non-computer engineer, it's two things. It's a tool which they program to solve problems. And by the way, most engineering programs have MATLAB as something that they need to solve problems. MATLAB is just another language. But because these engineering students have no clue as to what's going on, they use MATLAB in a very cookbook fashion. If they were to start by understanding how the computer works, and then programming it in zeros and ones, and then assembly language, and then C, and then MATLAB, they'd be able to write MATLAB programs that actually do useful things that go far beyond the cookbook boring stuff that they get in most engineering disciplines. So it's a tool to solve problems. Computers process algorithmically. What's an algorithm? I won't waste your time with describing the characteristics of an algorithm today. Most of you know it. But how many students in non-computer engineering know it? Computers process numbers. Can any number be represented in the computer? Exactly? Pi? I don't think so. 1/3? It can if you're using a symbolic representation. Most computers don't. They use numerical representations. Now lately we've got this sexiness called approximate computing. I would quip that Floating Point has been doing approximate computing forever, for example. The tool that the civil engineer needs in building the bridge. It's also an embedded processor, the computer. And you'll be pretty hard-pressed to pick any system designed by an engineer today that doesn't have an embedded processor buried in it. And if you don't understand sensors, stored program, actuators, you're operating in the last century, not in this century. What an engineer needs to know is how the computer works, how the numbers are represented, what an algorithm is all about. You start an algorithm, take the largest prime number. There is no largest prime number. So the steps in a computer program have to be effectively computable. Starting with the largest prime number, no. But if you don't understand this stuff, then you're back in the last century. This stuff we can teach a monkey to do. And should not be, in my view, given college credit for learning Excel or how to use Word. In fact, my secretary can make Word stand up and dance, and I'm still using the very basic elements of Word. Web browsing, rote learning of programming. Why introduction of programming in X is the wrong answer? It's almost always top-down. And when you're going top-down, you're not learning, you're memorizing. In fact, that's my mantra. Bottom-up. Build on what you already know. Effects of memorizing is that students don't ever get it. If you're not 100%, then you can't figure out where you went wrong. It's a cookbook education. remember I did a talk at Yorktown Heights, IBM in Yorktown, and for personal reasons I flew into Newark, picked up a car, I had to get to close to Yorktown to the hotel at 3 o'clock in the morning. I said, how am I going to do that? You don't want to be driving in New York State along these highways looking at a map while you're driving. You'll never reach your destination. You'll be dead before you get there. So I said, I'll memorize. Went to MapQuest, got the 18 instructions on how to get from Newark Airport to my hotel, and I memorized it. I get behind the wheel, and I start out, and I got the first 11 steps in the 18-step procedure correct. And I was within 3 miles of my hotel at 3 o'clock in the morning. And then I made a left turn instead of a right turn because I had not memorized it correctly. I memorized it 95%. But that other 5% got me driving around in circles for the next 2 hours looking for my hotel. I finally said, okay, screw it. And I went to the police station and they told me where the hotel was. If it's not perfect, it doesn't work, and the problem is if you memorize it, you can't figure out what you did wrong. My way, the student can figure out what he or she did wrong and can correct the mistake. And this MATLAB thing, which I'll belabor, more than once, no insight into how MATLAB works. What a shame that these kids in engineering are using MATLAB. They have no idea what they're doing, but they're getting these pretty curves because they follow the cookbook instructions. How much more they can do if they understood how the computer works and they get to MATLAB as a natural progression because it's just another language. Provides no insights into trade-offs and state. So if I had to pick the half a dozen things that I think is most important in a engineering education, it's the concept of state. That's what we do. You're in a state, you get inputs, you go to a new state. I don't care whether you're a civil designing a bridge, and the state is the amount of weight on that bridge, or whether you're designing a computer, and you're in the process of processing that single instruction. You've already fetched it, now you're in a state where you're ready to decode it. The concept of state is just pervasive in computing, it's actually pervasive in all of engineering. The notion of trade-offs. Trade-offs is what we do with engineers. The fundamental thing we do as engineers is design. There's no right answer in design. It's all about trade-offs. You want it cheap or you want it fast. Example of a trade-off. We do trade-offs all the time in engineering. And in studying how computers work, there's so many examples of trade-offs. You put a cache associated with the processor, big cache or little cache. That's easy. I want an infinite cache, single cycle access time. Can't get it. Caches are either big or they're fast. They can't be big and fast both. It's a trade-off. And trade-offs is at the soul, I say engineering. Is it engineering or is it a science? It's engineering. You want it to be a science? Okay, it's a science of trade-offs. That's what we do. Why Intro to Computing, which is the course that I want to talk about, is essential for all engineering curriculum. And this, too many departments are saying, I guess they need to know something about computing, so I'll give them a course in Java. Or there's one department at my university where they give them a course in artificial intelligence. I'm not sure what good that's going to do, but computing is a core competency today. Nobody quarrels with the notion of physics and math being core competencies. Every engineer will understand physics and math. In fact, we'll have the math department, the physics department teach them math and physics. Because we know, and we don't use math every day, we all understand math, we're all good at it. It's you assume the guy's an engineer, the woman's an engineer, that person understands mathematics. Do we use it every day? No. But it's in our toolbox, and when we need it, we better have it. If you can't do math, you're not really going to make it as an engineer. Physics, you have to understand physics. You also have to understand computing. In This century, computing is a core competency like math and physics. And I've already given you the tool and the processor. Engineering is about design. Students can have a meaningful design experience. Programming, by the way, real programming is design, by the way. You have a problem, you want to solve it. You got a clean sheet of paper. You need to design an algorithm to solve that problem. That's design, and there are trade-offs involved. You know, if you go back when you took high school algebra, there were two kinds of students that took high school algebra. Those students who could do, I don't know whether I remember it anymore, x equals minus, I've forgotten it, divided by the square root of b squared minus 4ac, that part I remember. You know, solving the root of a quadratic equation. You remember that? I don't remember it, but I remember there was a formula. And I do remember the square root of b squared minus 4ac was in that formula. And there were students who would always get that right. But give them a word problem. You got a bottle of stuff and it's 97% alcohol. How much water do you add to make it 95% alcohol? They fall flat on their face, not the engineer. Because the engineer is into solving problems. We used to separate the students, you know, based on, you know, could they do the word problems? Because that's what design is all about. Engineering is about trade-offs. I already said that. Engineering is about state. And there are lots of examples. We'll talk about some of them. An active learning experience in the freshman year. The student programs the computer from scratch. Zeros and ones. The program doesn't execute. Why? Because the student's made some mistakes. The student debugs his or her own program. And then the thing works. Why? The student succeeds. That's an active learning experience. I understand active learning has been used for different meaning in the educator circles, but I consider that an active learning experience. Engineers want causal deterministic systems, and that's what computers are. Everything should make sense. Okay, so how do we get here? So that's my little pitch on why, if you happen to be a professor of civil engineering, you should push for this course. In fact, you know, I don't know how many of you, you want to drive onto this bridge, and you get to the entranceway, and there's a red light saying, no, you can't go on the bridge. Why is there a red light? Because enough cars have tripped over the wire. There's a little stored program keeping track of how many cars are on the bridge, and if there are too many cars on the bridge fails, and so everybody goes into the sea or whatever. And so this little embedded processor is keeping track of how many cars on the bridge, and that's why that light is red, so you don't add to the weight on the bridge. So something as simple as a bridge, what could be more core civil engineering than that? I don't even want to begin to talk about aerospace engineering, you know, where it's so computer controlled, it's ridiculous and mechanical, even civil engineering. So how do we get there? Top down versus bottom up. In karate. So when you study karate, the first thing you don't do is learn the fancy katas. The first thing you do is you start with basic elementary moves and you practice and practice the single move again and again and again. Then once you get that, then they go on to the katas. You want to learn how to play the piano or the guitar. They say, here it is, Beethoven's Fifth, start playing. No, you start with these simple finger exercises and you continue to grow and you continue to build on what you already know. In football, you guys do play football at A&M, right? You did last year, we'll see whether you do next year. You know? And by the way, he's a pleasure to watch on the field, I will say that. And he wanted to go to UT, you know. I don't get it. Anyway, before you ever put on the pads and actually have a scrimmage, there are these drills you go through, getting ready. We build, not in computer science and engineering. Start with Java. And work your way down. Eventually you learn how the computer works, maybe when you're a junior. So you memorize. Aha! In fact, in Michigan, when I taught this course, what I did, giving ahead of myself, I'll do some of my out-of-order execution of my talk, which I end up doing all the time, is it was a faculty meeting, and the faculty were upset that the kids were not getting it. They didn't understand pointer variables. They thought that recursion was magic. I said the reason why recursion is not magic, and the reason why they don't understand pointer variables is very simple. The value 6 in location 4 is not the same as the value 4 in location 6. Pointer variable is nothing more than the value stored in the location as an address. If you understood the memory model, that I have locations and there are values in there, and you say there's an address here, and it's telling you where the data is, the mysticism of pointer variables goes away immediately. I said, if you want, what I can do is change the freshman course to teach them this stuff, so that then when you get them in the later courses, they will get it. And they said, wow, senior faculty member wants to teach freshmen, sure, let them go for it. But the results were fantastic. If you start at the bottom and continue to build and build and build, the kids can internalize it and they can get it. Why do we do this top-down? I think there's a misunderstanding between design and learning. Design should be done top-down. You want to do a new design, you start with a clean sheet of paper and you look at it top-down. You already understand the components. You already understand the underpinnings. And now you put it together in your new design. If you do design bottom-up, you end up with the old design with a pimple on it. If you start top-down, you have a clean sheet of paper, and now you can bring to bear everything you know. You already know the components. So design you can do top-down. You're not memorizing. Okay? Learning is different. Learning, when you do top-down, you don't know the underpinnings. You're at the mercy of what's going on. Another reason why they say that they want some high-level language is glitz. You know, you can wow the students with these fancy programs. The kid doesn't have any idea what's going on, but there are colors going and bells going, and wow, you can impress your, I don't know, girlfriend's father or boyfriend's mother or something or other. You don't need glitz. In fact, there's no glitz in my course. They write a program, a game program actually, to play the game of NIM. I don't know whether you know NIM or not. It's usually played with matchsticks. You have 3 rows of matchsticks and it's a 2-person game. You can remove some of the matchsticks, as many as you want from any one row. And then the person who removes the last matchstick loses. And there's no glitch there. They write the program just before Thanksgiving actually. So when they go home for Thanksgiving, and the parent says, okay, so you've been at the University of Texas for 3 months. You know, what'd you learn? He says, let me show you. Powers up the computer, and they play NIM. And we don't use matchsticks on a computer. What I got is 3 rows of X's. And what you do is you type a letter, A, B, C, that's the row. You type a number. That's how many matches you want to remove from that row. And you go back and forth until somebody loses, and prints across the screen, you lose, or A wins, or whatever. And the parent is impressed, and the kid is hooked. Wow! You know, so you don't need glitz. You need something that works. You need to understand what's going on. Maybe it's easier to find instructors for Java. I don't know. One big thing is the want ads. They ask for Java programmers. When you graduate, you get a job as a Java programmer. But the kid's a freshman. He's not going to graduate for 4 years. By the time the student graduates, it won't be Java anymore. It'll be C#. Right? So we teach Java now, because when we get to Java 4 years ago, Java programmers don't. We should be teaching C#. We don't. We teach Java. That's what the one had to say. 4 years from now, we'll be teaching C#. But that student won't graduate for another 4 years, will be B flat. Right? So this following the one ads. Object-oriented is a productivity enhancer. Absolutely true. I mean, absolutely true. The higher the level of abstraction that you're working at, the better. For getting the job done after you understand the material. I was in Manhattan. I don't know how many of you know Manhattan. This is the Manhattan. It's in New York, not Kansas. And I was in the financial district, and I needed to get to the airport. So I get in a cab, and I say JFK, 3 syllables. What could be a higher level of abstraction than that? And so what does he do? He takes me up the East Side Highway, over the Triborough Bridge. So as we're passing like 59th to 60th, we've already avoided the tunnel, we've already avoided the 59th Street Bridge. I said, what are we doing? He says, oh, I'm getting you the best way to the airport. See? If I operate at the highest level of abstraction, I don't understand what's going on. I'm at the mercy of whatever is going on. And of course, I almost missed my flight, and the fare was much too great. It's because he thought I was an out-of-towner, I didn't know New York, and so he said, and I can take him up to the Triborough Bridge and all the way down instead of doing this. You're at the mercy if you don't understand what's going on underneath. Once you understand what's going on underneath, then absolutely. I mean, it would have been a pleasure. I get in, I say JFK, high level of abstraction. I can sit back and read the paper and I glance out just to make sure that we're on the right road. That's much better. I hate when I have to go to the airport, get into a cab and say, okay, turn on the key, okay, pull out of your parking space, okay, get out of the block, make a right turn, now make a left turn. Sure, that would be absurd. So you can be much more effective operating at the high level of abstraction, providing you understand what's going on underneath. Former colleague of mine from Michigan who's now at Riverside, information hiding is all very good, but students need to first have some information before they can start hiding. How I made it happen at Michigan, the fact that you're unhappy because students weren't getting it, I've already told you that. I gave you the examples of pointer variables and the example of recursion. And you know, recursion, that'll blow them away, but if they understand, you know, there's that test that you do before you recurse. And it turns out that if you start from the bottom and you show them what's really going on, recursion is nothing more than a function call where the target of that function call is back to the start of the procedure. And you need the stack to push things on, but you already understand stacks because you're teaching them how the computer works. And by the way, recursion is not, so when I teach recursion, I don't teach factorial. That's a stupid way to teach recursion in my view. Because you would never do in fact, most compilers, if you do recursion, you know, tail recursion, they will turn it into iteration themselves, the compiler. Because they know that's not the right way to do factorial. Or Fibonacci. Or the example I came up with, which was Fibonacci, you know, which is yet one more. You know, Fibonacci of n is equal to Fibonacci of n minus 1 plus n minus 2 plus n minus 3. And then do that. And so when I was teaching at Berkeley, and I was teaching the machine structures course, which is essentially assembly language programming, but understanding how to, and by the way, we teach assembly language programming not so they will become experts in assembly language. If we want them to be experts in assembly language, we teach it as a graduate course. We don't teach it down low. Why? The purpose of assembly language programming is to understand how the computer works. And so I got this example of Fibonacci. Kids in my office, and we write the little program, and we do it recursively. And so you can type in your value for n, go off and have a cup of coffee, come back, and it still hasn't given you the answer. Now you write the program iteratively. By the time you get your finger off the keyboard, the answer is on the screen. Recursion is a powerful technique for handling this messiness. But you would never want to do it if there is no messiness. Fibonacci is no messiness. Factorial is no messiness. I have an example that I teach from with recursion is a maze. So I have a maze. And, you know, a collection of rooms, and there are doors, and you're in a room, there's a door to the north, there's a door to the east, there's no door to the south, there's no door to the west. How do I get out of the maze? Recursively is an obvious way to do it, and it all plays out nicely. You never want to try to do that iteratively. You couldn't keep the complexity together. That's where recursion pays off. You understand how the computer works, and you see the performance penalty of recursion, and then it becomes clear when you use it, when you don't use it. How I made it happen in Michigan, build on what you know has a nice ring to it. My objectives in the first was get rid of magic. And there's no magic associated with pointers or recursion, if you explain it right. Build a strong foundation, continually raising the level of abstraction. Abstraction is great. Some people say, I don't like abstraction. Of course I like abstraction. How can I not? No. But I need to get there. And the bottom there is my book. The McGraw-Hill rep for Texas A&M met me outside, and she wanted to stay to hear this thing only because that's pejorative. Maybe she felt that she could better market my book if she heard this talk. I have written a book, so I do have an economic interest, and because of that, you can discount everything I say. I did not write the book to make money. In fact, if any of you have written a book, if you know the number of hours it takes, you're working at below minimum wage. You know, even if Obama gets his $10 minimum wage thing through, he still will not be working at minimum wage and writing a textbook. I didn't do it to make money on the book. I did it because I think this is the right thing to do. But, full disclosure, written a book. Start with what they know. So what do I do in this first course? I don't start with quantum mechanics. People say, if you really believe in starting at the bottom, start with quantum mechanics. Two good reasons why I don't start with quantum mechanics. First of all, I don't need to. I can start with the transistor as a light switch. Kids have been turning on lights forever. In fact, what I got here is a piece of jewelry. Intel believes that all wafers coming out of their fab should have 100% yield. And the way they get 100% yield is they test the chips. Some go into laptops, some go into keychains. 100% yield. This is a Pentium chip. 3 million transistors. And these transistors are acting like wall switches. You know, you bias the gate one way, you got to open, you bias it the other way, you got to short. That's a wall switch. And that's where I start. I don't need quantum mechanics. I said there were two reasons I don't start with quantum mechanics. I don't understand quantum mechanics. Physicists tell me that it's real. I trust them. But I don't understand it, and I don't need to in order to teach how computers work. So I start with the transistor as a light switch.
Should we apply recursion to that?
I'm sorry?
Your statement before, should we apply recursion to it, to recurse on this thing? You don't need to understand quantum mechanics.
I'm sorry?
You said you do not need to understand quantum mechanics.
Right.
You can explain the computer without that, but if we recurse on this thing,
I knew there was a problem in having you sit over there. You can't keep them under control. So choose a computer model that is simple. You know, as what's his name said, make it as simple as possible, but not any simpler. Continually build on what they know, continually raise the level of abstraction, memorizing only what they have to memorize, trying very hard not to introduce magic. My approach, bottom up, motivated bottom up. In fact, I was with, Mike Clancy, who is a serious educator. He was one of Knuth's students and then decided he was more interested in teaching than getting a PhD, and so he dropped out of the Stanford PhD program and ended up teaching the first course at Berkeley, and he's been there I don't know, the last 30 years, 40 years, 30 years, I guess, teaching the low-level courses. I saw him at one of these computer science education things, and he said, you know, your book is intriguing. I've looked at it, and I think it's really neat, except that how do you keep their attention, you know? They want to know the overview, you know? How do you're in the bowels of the thing. How do you not bore them? And I said, I never thought about that before. And I went back, and I looked at the book, and I said, it's not the bottom-up approach, it's the motivated bottom-up approach. So I start with an overview. You know, what is computing all about? I'm not teaching, I'm motivating. Then operations on bits and bytes. Now I've got them ready that I can introduce the transistor. And once they understand the transistor, the switch level behavior transistor, we can do digital logic. And once they understand digital logic, we can do a finite state machine. And then we can do the von Neumann model. And then I can do the LC3 instruction set, which is a very simple computer that I've designed for pedagogical purposes, only 15 opcodes. I don't need 200 opcodes, 15 are enough. I only have one arithmetic, add. You want to subtract, take the negative and then add. You want to multiply, add. Right? And two logicals, and a not. So with 15 different opcodes, I have a rich enough instruction set. It's like Einstein said, keep it as simple as you can make it while still keeping the soul of the concept. I was in a PhD thesis proposal exam yesterday. The kid was out operating in this high level of abstraction. I couldn't get it. And the other members of the committee couldn't get it either. I said, you know, what you got to do is come up with an example that is as simple as possible, but yet retains the characteristics of the point that you're trying to make. And that's the idea. Now, once they get to this point, now we're ready to program and debug. They debug the first program they ever write. One of the reviewers of the textbook at the beginning said, why do you teach debugging so early? You don't need to know how to debug until you've written a 1,000-line program. Wrong. You learn how to debug with the first program you write. And then it's part of your how you do things. And then assembly language. And then data structures. First course, and they're manipulating data structures, where the data structures are actually what they look like in memory. Our Knuth. Knuth, if I have any hero in this business, it's Donald Knuth. And in fact, I taught data structures out of volume 1, a long time ago. Now everybody does it at a high level. That's wrong. And of course, Knuth agrees with me, but, more people do it the other way. No, so with the freshman course, linked lists, they see the links with pointers from here to here to here. We break linked lists, we insert into linked lists, we order linked lists, string arrays, character arrays, trees. You can do that in assembly language. Physical I/O, they do physical I/O. You hit a key on the keyboard, and the computer takes the ASCII code of that key and puts it into a I/O register and sets the ready bit. So you can do on the program control spinning until you get that ready bit. Once you get the ready bit, you know the data register's been loaded, you can grab it and do whatever you want with it. Now the operating system usually takes care of that for you. That's fine. We have operating, in fact, I have a trap. One of my 15 instructions is a trap instruction. You do trap with a trap vector. You want to do I/O? Fine. You do trap with the trap vector that says get a character. Which means sit there, print the banner on the screen, and the operating system does this, the trap routine does that for you. Print the banner on the screen, input a character. And then it sits there spinning until somebody hits a character, loading the data register, setting the ready bit, and then the routine takes that ASCII code, puts it in the register 0, turns control back to the program that asks for the character. And now we got the user program interacting with I/O, physical I/O, using the operating system. And when they write their first program, they use a trap instruction. But before the first semester is over, they understand how these operating system routines actually work. Interrupts. Interrupts is no problem either, and we have an interrupt enable bit, so that when you hit a key, it will interrupt the program that's running, go through the service routine, and then can turn control back to the running program. And their last programming assignment is to have two programs. One is a program in an infinite loop, which is continually refreshing the screen with something silly like a checkerboard or something. And it just continually does that until somebody hits a key. The other program they write is the interrupt service routine. So they write the program to keep refreshing the screen, somebody hits a key, causes an interrupt, the interrupt service routine then grabs that key, and prints on the screen that character some number of times, and then returns control back to the running program. So what you end up with is, here's a screen, and the continually refresh infinite loop that it's going through. Somebody hits a key, all of a sudden you see this character string, and then it goes back to refreshing the screen again. And they see how in the first semester, freshman year, they're doing that. Interrupts, no, never again will be magic. They see the connection. So program, so what I got, number 11, physical I/O traps and interrupts. And then we're ready for a high-level language to teach them. High-level language. So I picked the lowest of all the high-level languages, C. And when we teach C, programming in C, every time we do a C construct, we show them what the computer would be doing if we had written that construct in assembly language. And so, in fact, pointer variables. In my instruction set, I have an instruction called LDI, load indirect. What load indirect is, it goes to a memory location, and what it finds there is the address of the data. That's a pointer variable. At Texas, we teach the whole thing that I show on the screen here in 2 semesters. First semester is up to the point of C. Second semester is C. I teach the first course. And so kids come back to me during the middle of the second course, and he says, you know, we're sitting there, and the instructor is going to a whole hour to explain pointer variables. And the kid sitting next to me says, why doesn't he just say LDI? And in 15 seconds, and he's taught us pointer variables. By the way, the machine is called the LC3. I think I'm about ready. No, I guess I'm not ready yet. So here's a picture of memory. Yeah, go ahead.
On that previous slide, I'm just curious, where do you bring in memory? Where do you bring in the concept of memory?
So the von Neumann model. Yeah, is where we bring in memory. So in fact, if you've seen the book, it's chapter 4 of the book, and we go through the instruction cycle, you know, fetch, decode, etc. So you start with von Neumann. Von Neumann says, okay, what have I got? I've got memory. Memory is what makes things different. Computers are different from radios, for example. Although today, you've got memory in the radio also, because what you really have is a microprocessor controlling the radio. But the old days, you didn't have that. It was just picking signals out of the air. The thing that separates computers from other electronics initially was that computers had memory. So the von Neumann model is it's a good thing. So that's when you talk about memory. In fact, the example I just gave you of 4 is in location 6 and 6 is in location 4. I got a figure in the book that says exactly that. And so you got memory, you got a computation unit, ALU, temporary storage, registers, input and output, and then control is controlling the whole thing. And you go through the instruction cycle. Then you're ready. You've already understood finite state machines, because that's what computers do, is they go through a state machine. I got a picture of a state machine here. And now you're ready for the LC3 instruction set. Here's a picture of memory. And they are, by the time, and this is like at the end of the digital logic section. And so you see up in the top left it says A10, that's the address, 2 bits of address. Because I got 4 addresses, 4 locations. Each row is a word. It's not 64 gigabytes of memory. It's 4 trips of memory. That is to say, there are 4 locations, there are 3 bits in each location. That's why you have 12 latches on the screen. At each of these 4 locations, you're storing bit 2, bit 1, bit 0. So you need to know at what address are you reading or writing. Those are the address bits, which go into so the thing on the left is a decoder, which tells you which of the 4. And those 3 things on the right are muxes, which tell you which bit to pull out that you're reading, right? And by the time you get there, you've had the transistor, you got digital logic, now you got muxes and latches and decoders, now you're ready to do memory. And then you do finite state machines, and now you can put it all together. And it's really like 2 or 3 weeks, and they get it because you're continually building. Here's the instruction set. As I said, only 1 arithmetic, add. You see over there are 2 rows for add. And if you look closely, you'll see that so it's a 16-bit instruction. Bit 5 is a steering bit, which tells you whether you're adding register to register or whether you're adding register to immediate. Most machines have this concept of immediate literal addressing. And so I decided to put it in here. It didn't cost me anything, so why not? and two logicals, and not. And so he lied, get away with one logical, NAND. It's logically complete. Yeah, but it's not intuitive. And I'd rather be intuitive. And so I wasted two opcodes for logicals, and not. As a conditional branch on condition codes, as a subroutine call, there is a jump to a register instruction, indirect jumps. There's a trap instruction, which I already gave an example of for I/O. There's a return from interrupt instruction, because interrupts are different. When you take an interrupt, you push on the stack, the process and status register and the program counter so you can come back. So, and the rest of it is like a half a dozen instructions, which 3 loads and 3 stores based on 3 different ways of addressing. Indirect addressing, load indirect and store indirect, load PC plus offset and store PC plus offset, and load register, base register plus offset. So I waste a lot of the offload space for these addressing loads. And that's it. And it fits on, so if you see the book, it's the inside back cover. They can grok it, there's no hundreds of opcodes. There's enough. It's very rich, but there's only 15 opcodes. Turns out originally there was 16, because the way we do a subroutine, we do the old, in fact, the ARM ISA, which has become very, very popular these days, does a subroutine called the old IBM way, which is to store the link back in the register. So that's the way we do it. I didn't realize it. So I came up with this around the same time that ARM was coming up with their instruction set. So you need to be able to return, and return is simply to take the contents of that linkage register, which we use one of the general purpose registers for, and load the program counter with that. And then this freshman raises his hand and says, why are you wasting an opcode on that? Why don't you use the indirect jump instruction for that purpose? Where you hardwire the register number to be that register that you're using as a linkage register. Yeah, got rid of that opcode, decided not to replace it, but make it a reserve for future use opcode. And that happened quite some time ago. And every time he needs a letter of reference, he reminds me that he was a freshman who told me that instruction. So the ISA is very simple. One page, that's the entire instruction set architecture. Here's a data path. All the structure that I need in order to process this instruction set. Look what you got up here. You got an adder that controls a finite state machine, register file, boxes. There's very little there. They can grok it, they can understand it. Here's a state machine for the whole thing. Okay, I think I'm going to skip the ISA business because we're running out of time. I can come back to it later on. What I've done is I've made an analysis about which instruction set architecture should come first and which programming language should come first. And I think I don't have time to belabor it. The biggest takeaway is the first ISA, not the last ISA. By the time they ISA instruction set architecture, by the time they graduate, they'll probably know several. What's important in the first one is that they understand what an instruction set architecture is and how it works. And because I've designed it from scratch, I can do it pedagogically rather than adopt a real instruction set architecture, which has all the uglies caused by the fact that people in industry designing it for real are interested in the economic advantage, and there are a lot of kludges and stuff that's in there that they're just going to waste the time of the student. Okay, so why we chose a real ISA is not without glitches. We can make the decision pedagogically. Okay, so how it evolved. We started with the LC1 when I was teaching computer organization in Berkeley, and I only had one register, a single accumulator. This was back in the days when registers were very expensive, as many of you know. One condition code, which you can't program. With an accumulator-based machine, it must have been a nightmare for programmers, 60 years ago. So then I came up with 4 registers. I was co-teaching the course at Michigan when I introduced what we called the LC2 with 4 registers, and my partner who was teaching the programming part said, you know, 4 registers really aren't enough. You know, we want to do procedure calls, and build stack frames, and by the time we run out of all this bookkeeping registers, I've run out of registers, so can you give me 8? I didn't want to give them 8, because if you double the number of registers, you've added a bit to the identification of the register, and that chews up. I wanted to keep it a 16-bit instruction, but finally I said, okay, you're right, you need 8 registers. So I need 3 bits for the first source register, and 3 bits for the second source register, 3 bits for the destination, 9 bits of my instruction are chewed up. But it was worth it, because he couldn't do serious teaching of the programming part with only 4 registers. And then we made some changes. Initially, I had the stack go from 0 up, because I thought students could understand that better than have the stack go from high down to 0. And it turns out I was wrong. Students can figure that out. And all real machines build the stack to 0, so I made that change. I also thought that having the program, it was an old PDP-8 trick. I don't need to tell you about it. It was a mistake. Now PC plus offset rather than concatenating the high bits, the page bits with the rest of the address. And now the next thing I'm doing is making privileged memories more serious, because people want to write operating systems for the LC3, and until they have privileged memory in a real way, they can't do it. People are already writing compilers for the LC3, so why not give them that? We left out endianness. It's word addressing. 16-bit instruction takes up 1 location in memory. Most machines are 8-bit addressing. But once you do 8 bits, then you have to worry about big endian or little endian, and that I felt was something that I didn't want the freshmen to have to worry about. It's silly to make a freshman who's trying to get it worry about endianness. By the time they get to be seniors, they take the senior course, which has them design and build the LC3B, which is a byte addressable LC3. I put endianness in. I got rid of lots of data types, no floating point. I got rid of lots of addressing modes. I told you the only ones we have. And I only have what I think are essential opcodes, and I've already told you, the add and the 2 opcodes. There's continuing pressure to add a multiply, because to multiply what you need to do is write a routine. You want to multiply 5 times 4? Okay, so you read in the 5 and 4, you clear a register, add 5 to that cleared register, subtract 1 from the 4, add 5 to the register, subtract 1 from the 3, add 5 to the register. Eventually this goes to 0 and you've got the product of 5 times 4. For those of you that are mathematically gifted, you know 5 times 4 is the same as 5 plus 5 plus 5 plus 5. So I didn't need a multiply, and I wanted to keep it as lean as I needed to. People want shift instructions. If you know about arithmetic, you know that the soul of integer arithmetic is having a clean way to add long integers, which means you need an add carry instruction and you need a carry bit. And they've asked for that. So far, I've not done it. What we've learned, don't succumb, keep it lean. A 1-page ISA these students learn. It can be rich without being complex. Rich, trap instruction, interrupts in the first semester. Physical I/O, all this stuff is rich, and yet the instruction set is just these opcodes. With simulation, you really can create the wow. I gave you the example of the NIM game. Some of my TAs, one of the good things, if you get great TAs, and I do, because I interview them extensively, they've added this other game program for the kids who really want to push it. So I was not a child when the game, 4 Square, is that right? Does that make sense to you? It's a game where you have 4 columns and you keep adding to get a row or a row. Connect 4. No?
Yes.
Connect 4, yeah. So we've introduced that game into the freshman course. And some of the kids actually write that game rather than in-game, which is like 10 times as much work. But when they get home on Thanksgiving, I do it intentionally just before it's due just before Thanksgiving. So when they go home for Thanksgiving, everybody, this is America, everybody goes home for Thanksgiving, right? And so you go home for Thanksgiving, okay, what'd you learn over there? Let me show you, you know. Wow. Follow on, the LC3B is what we teach in the senior year, the bite-oriented. I get rid of the LDI and STI in the LC3B. The LDI, load indirect and store indirect, are in there in order to make pointer variables a piece of cake. It's worth it to me to waste 2 of my 15 opcodes to make that happen. By the time they get to be seniors, if they don't get pointers by then, it's too late. So I get rid of LDI and STI, and in the LC3B it's replaced by load byte and store byte. Because now they want to know about endianness, because real machines care about it, and they also need to know about byte addressable memory by the time they get to be seniors. So the LC3B is a richer version. And people are designing this LC3 in their VLSI courses, and some people written compilers for it. The LC3B, the senior course I'm talking about, is taken by seniors and first-year graduate students from other places that haven't had a hardcore architecture course. What the students do in that course is they start with this LC3B, which I've given you most of the flavor of it, and then they add virtual memory to it, and then they add interrupt and exception handling to it. So they increase the state machine required to make it closer to what a real machine is. But that's for seniors, and we're talking about the freshmen. Instead of having a not instruction, I replaced that with the exclusive OR. And it turns out I designed the not instruction in such a way that if I take the exclusive OR of a register at all ones, what do I have? The not instruction. Right? Compatibility. Word addressing becomes byte addressing, LDI and STI is scrapped, and I also added a comprehensive shift instruction that allows you to shift any number of bits in either direction, either arithmetic or logical, but that's the LC3B. Okay, benefits of bottom up. We get rid of magic, minimize memorization, maximize understanding, because they are building on what they already know. They debug their own programs. I gave a lecture at, when I was at Michigan, I gave a lecture at Michigan State. And I said, you know what these kids do? Says, you know, you graduate students that have never written a program in their lives. Never written a program. Not us. I say, yeah, you know what the kid does? He writes a mess, goes to the TA goes, ugh, and fixes the first half of the program. He said, now you finish it. What does the kid do? Goes to the other TA. So he graduates, he's never written a program in his life. And so the professor, you know, you see the carotid artery, you know, pulsing. He says, oh, we have a senior project where there are 3 students in a group. No, we have a senior project where the students write the program and they're not allowed to get help from the TA. And they write the program completely by themselves. And I say, really? And they do this alone or they're in groups? So what? Oh yeah, it's a 3-person group. I said, oh, okay, that's easy. 2/3 of your graduates have never written a program. In this course, they debug their own programs because they can. Because when they make a mistake, so what we have is an LC3 simulator, which they load up, they single step, they set breakpoints, they deploy very low-level ODT debugger. So they can put values in registers in memory, they can single step, they can set a breakpoint, run for a while. And so if the program doesn't run, they go back and debug it. They do it. They don't need us to do it for them. By the way, I should mention that there are a couple of faculty, and I don't know whether they're in the room, whose sons, so shame on them. Instead of having their son come to A&M, they sent their son to Austin for graduate school. And they've been in my course, and they've done extremely well, and they love it. So my best marketing people to do the course at A&M correctly would be to talk to the sons of these 2 professors. I don't know whether they're videotaping, I'll leave their names, but I'll tell you privately who they are. But there are 2 professors at EE here whose whose sons have taken the freshman course with me. And every time they see me, it's like, wow, thank you, Dr. Patt, for what you've given us. They fund their own programs because they can. They end up with a broad-based foundation in logic and how the computer works. And they love it because they get it, and the teachers love it because the students get it. And I get email all the time from people, about 100 schools that I use in the book. And the email is just, I've never had somebody who's used the book tell me that it was a bad idea. They just, you know, it's like 100%, literally 100%. You know. And it is a breadth first introduction to computing. And I've got a list of all the things that you get in this book. Interaction of the application software with the operating system. The first semester, powerful. What I learned about freshmen, about students. Freshmen can handle serious meat. There are some schools that waste a freshman course because they figure the freshmen aren't ready to think. We need to spoon feed them. They're still in high school. They are still in high school even though they're carrying a university ID with them. But that's part of my job. Knock that out of them. And I do. I waste a lot of time knocking high school out of them. I tell them that I'm going to teach them that they're going to have to think on the exam. In class, I tell them how to get from A to B. In class, I tell them how to get from B to C. On the exam, I'm going to ask them, how do you get from A to C? If they memorize, they'll never be able to put it together. And the first exam, and the average is like 30 to 40, because they've memorized everything, you know? Open brain, insert material, close brain, hope it stays in there long enough to pass the exam. And then it can forget it. I won't buy into it. Freshmen can handle serious stuff, and if you set the bar high, the good students will measure up. And the bad students, well, they're videotapers. So students don't need glitz. Good students want to know what's underneath the hood. They want to know how it works. Computer organization, how the computer works, let's start with freshmen. And the bottom up eliminates the memorization, and so you don't get this thing that is 95% perfect, but they have no idea what is going on wrong. Good students memorize, by the way, only for only one reason. Okay, about education.
What is that reason?
Ah, somebody did. You'd be amazed at how many times I give this lecture and they'll just let it slide. Then I have to decide whether it's important to go back and tell them. They don't want to fail the exam. So the night before, when they can't figure it out, then the good student will then memorize in order to hope that they can then barf it out on the exam. I wish I came up with that on my own. I didn't. I was on a piano dealing with the stuff we're dealing with today. I can't remember what university it was. I don't remember anymore. But there was a professor of education on that piano. He said, by the way, do you know why students memorize? I said, teach me. And that's the reason. You know, this guy, his thing is education, period. He said, that's why they memorize. They don't want to flunk. You know? But a good student, if the student has it his or her way, they'd rather understand than memorize. About education, engineering education, there is no substitute for design it wrong. We all design it wrong. You know, that's how you learn. Debug it yourself. You fix it. And you see the working result. And wow, an engineer is born. Avoid the latest fads. You know, there's businesses, and there's, you know, look at the want ads, see what they want, and teach to the fad. That's not our job. Our job is to teach a foundation that they're going to be able to have good for the next 40 years. And today the pressure is Java, and next year it'll be C#. I already given you my joke about D flat, nobody laughed. You're a tough audience. Abstractions are great after you understand the underpinnings. Serious programming is about design. First, understand the components before you can design. Scheme, by the way, some people think scheme is a top-down approach. It isn't. It's a bottom-up approach. The thing about scheme, what they're pushing is algorithms. And so they start with the scheme language and they move up from there. So even guys, and those guys are good. Sussman and Abelson are just absolutely brilliant educators. MIT, by the way, is a great place for education. So they have shipped this to MIT, let them pay more royalties on their freshman admits. They really do care what the students learn in the freshman course. And these two guys, Sustin and Abelson, have built this 6001 course, which I understand is going away, which I think is a mistake, frankly. And the language is scheme. And what they're doing is taking the language, and the whole thrust is algorithms. You start with the language and you move up. That's the way to do it. You start and then you build. You don't start and then go down. If I was to teach data structures again, I would use Knuth. In fact, Knuth has written a little thing for my book, and it's like the inside cover. And he says something like, if you don't understand how these data structures are stored in memory and how they're actually manipulated, you will forever write bad algorithms. And I guess there's a lot of sentiment in the industry today is it's okay to write a bad algorithm. You know, it doesn't matter, just as long as it works. You know. I guess I like it to be an efficient algorithm. It'll be, you know, dependent, and it will win on whatever your design point is, performance or whatever. And I would teach that. I've taught data structures out of Knuth back. So I was taught at Berkeley for what, 9 years, and I taught, my first semester there I taught 2 courses, the data structures course and the computer organization course. And I did it intentionally because you get this thing, you know, I'm a hardware person, well, I'm a software person. I'm a person. And the more you know about both, the better you're going to be at doing whichever it is that you're being paid to do. And so I wanted to make that statement that I will teach data structures and I will teach computer organization. And you, the student, are going to have to learn both before you graduate. And you should really pay attention to both. One thing about this course, if you do decide to do it my way, and there's about 100 schools that are now doing it, gave a lecture at Cornell Education, are there any questions? And the department head, or chair, I don't know whether it's a head or a chair, but he was so taken by it, he went out and got a copy of the book, he couldn't put it down. They're doing it my way at Cornell. Wisconsin, they're doing it my way now. Santa Cruz. Illinois, but that doesn't count because my co-author is my student who is a full professor at Illinois. So that doesn't count. Texas doesn't count because I'm doing it. It's my way. But I think that Santa Cruz and Wisconsin and Cornell and Georgia Tech, and there's about 100 schools that are doing it. The Chinese are buying off on this. In fact, what they want me to do is come to China every summer and teach it to their freshmen. I've done it twice. I've done it at Hefei, the Chinese University of Science and Technology in Hefei, and I've done it at Zhejiang University. And these kids are amazing at what they're. I take the 15 weeks and I shrink it to 3. I can't believe it. And they actually master it. China's got something going for them. Ripple effect in the curriculum. If you do buy into this, you will find that subsequent courses are better because you can build on what they already know. You don't have to wave your hands anymore. They've got it. And you can make your more advanced course a better course as a result of it. And I learned that at Michigan right from the get-go. There's professors in the later courses thank me because they can see the difference. You know, when you first get started, some kids have had it, some haven't. And so the professors can see the difference between those who did it this way and those that didn't. Building this foundation early. Most of the material was from the junior course at Michigan when I started. And I asked the students, I said, how would you feel if you learned this as a freshman? And they almost unanimously said, yeah, it would have been great, because everything that we have taken as magic up to now would have been in our solid foundation. But it is going to change the later courses. Okay, everybody who does it seems to like it. Most importantly, after more than 45 years in the trenches, so I walk the walk. I actually do teach, you know. And that 45 needs to be updated also. So after more than 50 years in the trenches, amazing. And everybody else is getting older too, you know, except for me. A simple concrete model really makes a big difference. One of the problems I have with faculty is that we get it. You know, we understand how computers work. We've been doing it for a long time, and we forget what the freshmen are coming to grips with. We can think all we want about beautiful abstractions, but we're not freshmen seeing it for the first time. I'm done. So.
We're just gonna take a few questions, right? Because it's
Whatever you want. You can go as long as I don't need to eat, you know, so go ahead.
This takes me back to days of programming PDB-8s, and I'm glad to see you've updated to a RISC PDB-8. You said this is a 2-semester sequence. They do this and then semester C, is that right?
So what I've shown you here, so videotape still going. So in Michigan, it was 1 semester. And I came down here and they convinced me that we're not going to get this in 1 semester. So we made it a 2-semester course. Actually, the best format, I would say, is if you're on the quarter system and it's a 2-quarter course. There's too much material, whoops, I don't know what I just did. There's too much material in the course for 1 semester. In fact, I had the experience of your question with respect to the finite state machine and the von Neumann model and all that. I covered very not well, I feel, when I was doing it at Michigan, because I had 8 weeks to do the first half. And then my colleague came in and did the programming part in the last 7 weeks. And we did it 1 semester. And I didn't realize that I was skipping over some stuff. And then Trevor Mudge, senior professor at Michigan, he taught the course, and he said, you know, you think you're doing this, but you skipped a step. I said, Trevor, you just don't get it, you know. Well, of course he got it. I just didn't get it. I was rushing through it. So then I come here, and I got a whole semester to do the first half of the book. And so I'm doing it more carefully, and I all of a sudden say, wow, they don't have this underpinning. And so I added, in fact, it ended up being a couple of extra sections in the second edition of the textbook. It's really too much material for 1 semester. It is not, it's, for 2 semesters you can do a lot more. In fact, one of the things, if, you know, if it became required for all engineers, what I would do would be to put MATLAB at the, see, you do C and then MATLAB would be a natural thing. And they come out of that course with the foundation that they actually use MATLAB in a meaningful way. But the real answer is that Michigan was a 1 semester, and Illinois is a 1 semester course, the whole thing. At Texas, it's 2 semesters. We go through the first half of the book. We go up to the point of C. So the last programming assignment, the last problem that they work is they write, as I told you, a program that's running infinite loop and interrupt routine, and they get it to work. That's the place where we break it in Austin.
The problem I can see is that some department, let's say mechanical, says, great idea, let's do it, we're just going to do the first half and stop. And then the student has no marketable skill.
So he understands how the computer works. That's such a core competency for civils and mechanicals and aeros, etc., that he does have a marketable skill. I think what I would do, you know, if I had the luxury of the, and in fact, if we do eventually adopt it in mechanical at UT, what I could do is I could take out some of the stuff. So I would hand wave the digital logic, for example, and I would put programming in there instead of that. So you could take out some of that first half in order to give them the, so I'm translating marketable skill into being able to program. Yeah, so they can program an assembly language when they get through here. One of the best students I ever had in my life, Kathy. Won't give you her last name in case she ever watches, or her husband watches this, at North Carolina State. And she was fantastic. She graduated, and for reasons which there's no need to get into, instead of taking a job at the Research Triangle Institute, which I got for her, she decided to take a COBOL programming job. You know, working for Burlington Mills, textile. She didn't know any COBOL. How do you know she's gonna take a COBOL programming job when she doesn't know any COBOL? So she graduated in December, she's gonna start working on January 1, January 2. So what did she do over the Christmas break? Picked up a COBOL manual and taught herself COBOL programming in 2 weeks. You can do that. In fact, engineers are good at that. In the advanced course at Michigan, which was required for the CS students and the CE students, and they're designing a machine, what's the language I should use? Verilog. Absolutely clearly. Because machines work with concurrency, and if you want to do something sequential in a hardware description language, you have to say, "and." You have to actually make the statement saying that this and this really has to be done sequentially. I had a problem, right? The CS students didn't know Verilog. Well, you see, CS students know C. Well, I got a problem. The engineers, a lot of them didn't know C. So what am I going to use? Verilog or C? Answer, I use C. Why? Because if I use Verilog, and I don't waste class time teaching Verilog, then the CS students wouldn't like it. I realize I'm killing my audience here with this, but I'm going to do it anyway because it's. Talk to Bill Gates. He will reinforce this. If I teach C, the double E students won't like it. But what they'll do is they'll say, I gotta know C. They'll look at a manual, they'll teach themselves C. And that's what we ought to be doing in education, is give them the foundation, and then when they need something, she never needed COBOL in college. She's taking a job as a COBOL programmer. Now she needs COBOL. Get the manual and do it. Right? If you give them the foundation, then they can learn whatever they need to learn. And I'm not saying all CS students are of this kind. Too many of them are, and Bill Gates, what does he say? They have to interview 1,000 students for everyone they hire? Because the student can parrot. Now, I'm just a, egocentric electrical engineer, I guess, that engineering is the right education. But we do, we teach a foundation and then we build on the foundation. Anyway, I've gone on to a rant. You're right about the marketable skill. You're absolutely right that they may give you 1 semester, they won't give you 2 semesters. We have to do something to accommodate that. But
how would you compare what you're doing to Randy Bryan and David O'Halloran?
yeah, so I happen to be a big fan of both those guys. Are you using their book here? In what year of the student's education?
The computer science, computer organization.
No, I understand that, but freshman, sophomore, junior year? Huh?
Junior.
Huh?
It's what they do with their software.
Junior. See?
Software, actually.
So I asked the question intentionally to see what answer I would get. I would say they're not ready as a sophomore for that course. And I think if you really got Randy drunk enough, he would maybe agree with that. It's an excellent book. Those guys are excellent. They know what they're doing. So when Randy was writing the book, he asked me, because my book had come out already, he wanted to also think about actually getting the book. And we respect each other, as far as, technical, people. He wanted his first ISA, the ISA in that book is the X86. That's a nightmare. Do you know the X86? I guess you do. The first byte of the instructions, the opcode? There may be anywhere from 1 to 4 prefixes in front of that opcode. And it may not be a 1-byte opcode, it might be a 2-byte opcode. And the most important byte in that instruction is the mod RM byte. And then you may or may not have an SIB byte. And you may or may not have a literal or an offset of the as your first ISA, I don't think so. The reason why he's doing it is he's really more interested in the operating system stuff than he is in the computer architecture stuff. I personally think it's a mistake using that book in the computer organization course, especially if that's the first ISA you see. How would I compare it? Both of us want the kid to learn. I think I'm teaching freshmen. It turns out a lot of schools are using my book in the sophomore year, and some of them are Graw Hill people, and the rep was here early and gave me some cards if anybody wants a card of the McGraw-Hill rep for Texas A&M. I've got one here. I'm teaching it for freshmen. Some reps are marketing it as a computer architecture book. It's not. It's a fundamentals book. It's a foundation book. I don't talk about caches. I don't talk about virtual memory, and I don't talk about pipeline. How can it be an architecture book? So what a number of schools have done is adopted my book for the sophomore year and then added material on those three topics because you can't do a sophomore course without those three topics. I think Randy's book is absolutely a junior level book. And I'm not going to tell you how to do your whole curriculum. You know, if you think they can handle the sophomore year, more power to you, you know. But it's not easy for them to handle it the sophomore year. And I think part of the problem is x86. The reason he's using x86 is pure and simple. He wants them to write real programs on a real machine and test them running on the real machine. And the real machine of choice is the x86. Now, in fact, a good question I might ask him next time I see him is, with all this play that ARM is getting these days, are you going to move that book over to the ARM ISA? The ARM ISA, by the way, is a nightmare also. The ARM ISA is not what it was in 1985 when they first came out with it, you know. It's, in fact, ARM stands for what? The R in ARM is RISC, right? Yeah. No. If you look at version 8 and the formats of that instruction, you want to do a multiply on ARM? You didn't start out being able to do a multiply. They found that if bit 7 through 4 has a pattern 1001, you can use that to make bits 25 through 20 a multiply instruction. Nice and RISC, right? Yeah. I don't know what they're going to do. But the first ISA is not the last ISA, and I insist the LC3 is a better way to go. If you're going to use my book in the sophomore year, then you're going to need to add things like caches, virtual memory, pipeline. Because that's what I may do. In fact, what I'm thinking of doing for the third edition is writing an appendix that if you're going to use the book in the sophomore year, you do it. No, so your first question was what I think of Brian O'Halloran. I think they're great, and I think it's a very strong book. It's certainly not a freshman book. I would argue that it's not a sophomore book either, but if you're successful with it here, then, you know, you're a better man than I am. Okay? Yeah.
I don't know if I have time for another one, but I'm curious. So the one, I like this very, very constrained ISA that you have here, right? It's very similar to the way I was taught, actually, as an undergrad.
And you got it, right?
And yeah.
Yeah, you got it. It makes sense.
I guess my only concern is, what about tools, so tool support, in terms of compiler and you know, stuff that you want to build on top of this, or do you basically advocate kind of switching away to something that has...
Oh, yeah. So I want to get you started. I want to develop a foundation. Then when you get into the follow-on courses, you just build on that foundation. So the language, so what they do is C, and then at Texas, at UT, we do Java after that, you know. I would make Java be a one-unit senior course, like this, like my best student who, you know, took 2 weeks and read the COBOL manual. I'd make it a one. You're going to get a job, you're going to be a Java programmer, fine. We'll give you a one-unit course your senior year. But don't confuse that job-oriented thing with, you know, pedagogy, in my view. So the tools for this is the simulated debugger, where they can load up the program, and I told you, it's an ODT debugger, they can deposit, they can examine, they can set breakpoints. You know,
But what about for the C part of the class?
I'm sorry?
What about for the C part of the class? Do you have a C compiler, or do you just kind of...
Yeah, so for the C part of the class, we use a C compiler. And now they're programming on real machines. Yeah. Questions? Yeah, go ahead.
How will you structure a MATLAB when students, your class at the first requirement?
I'm sorry?
How will you structure MATLAB differently? I mean, when we teach MATLAB.
So I don't teach here, so I don't know how you teach MATLAB, but what my experience has been at many universities is MATLAB becomes a tool that they follow a cookbook thing in order to get the curve to look like the way it's supposed to look.
Basically, it's what we teach.
Yeah, and they don't know what, so the point is that if they understood MATLAB as a language, they can write their own programs to do whatever kind of data representation So you've done an experiment, now you want to show something. And MATLAB is a powerful tool for now being able to display information that you want to display, as opposed to display only information that the professor has decided must be displayed as a reinforcement for this one concept. So do you see MATLAB as a language? I guess that's my first question, you know. Because if you don't see MATLAB as a language, I mean, some people don't, you know, QuickBooks.
Actually, we see it as a tool to solve engineering problems.
But a tool that can only do the things that you tell the student to do, or is a tool that they can use for all kinds of display purposes? Right? That's the problem. Is that they're going to be able to do so much more with it than just, I want you to be able to show where it crosses the x-axis, you know. You can do a lot more with that. That's the point. Yeah, Lawrence?
Do you, assuming that this class is taught in 2 semesters, so there is, let's say, more time,
Yeah.
would you, and this is the fundamentals, would you add maybe towards the end something like an object-oriented language and walk the walk all the way up to,
You can do that.
and so that you understand that object-oriented is not in thin air, but it is actually maybe, you know, go to C to, I mean, the whole spectrum if you want.
Yeah, and in fact, what I would do is if I was doing it as a 2-semester course, which
Which is
I
exactly
don't
what I
want
asked.
to suggest this nightmare for you. I would say that you guys in computer engineering or computer science, I don't care where it, you know, where it sits. It could easily sit in CS, it could easily sit in CE. Would be responsible for the first course. The second course would be targeted differently to each major. So the civils would be programming bridges, and the mechanicals would be programming cars, and the aeros would be programming, you know, space stations or something. That is, the application space would play into the second course. And
But I think that it's too far away, what you're saying.
I'm sorry?
I don't think that in a second semester, somebody should worry what the application space is.
so I'm responding to his point, which I think is a valid one, in the second semester. You have enough that they can they can tailor the applications to things that they care about in their discipline. I mean, we do that already in math and physics, right? We give the students to the math department to teach them calculus. But then when we get them back, we then build on that calculus to problems that are specific to our own discipline, right?
Yeah, but
And the same thing with physics.
But we
And I'm
don't,
suggesting that computer technology is a core competency.
you don't give them to physics only 1 semester, or to mathematics.
Yeah.
You give them a heck of a lot more. Then you have enough fundamentals to build whatever you want. So if you're going to give it, what you're arguing, to computer
I
engineering
understand.
and
So
science,
obviously, yeah,
and you
so-
should give them 2 semesters and teach them the fundamentals from bottom to top.
So I guess what I'm doing is being a little bit more pragmatic. So yes, if I had it, so I think your way is the better way. If you can do that.
This is not pragmatic, it's only 2 semesters. You already said that you want it for 2 semesters, or 2 quarters would be the easiest. Now, if you have to have 3
quarters, so in
quarters,
fact it's taught, so a number of I assume at Santa Cruz it's done in 2 quarters. Riverside it's done in 2 quarters. Riverside was one of the first to adopt it. University of California. The UC system, most of those schools are.
you convinced Lakshmi.
Huh?
You convinced Lakshmi before.
No, actually, no. I convinced Waleed
I see.
while he was still at Colorado State. In fact, he's been using the book since before he came out. I had to sign a letter to Kinko's to reproduce the latte output so that he could use it in his class. Yeah. No, 2 quarters is right. If you do go to 2 full semesters, you've got the luxury of now being able to do more in the second semester. Yeah. And I was being pragmatic. I say, look, why not tailor it to,
It's perfectly tailored. If you teach them some higher level language on top of this class, they will bridge from the bottom, from the hardware, all the way to the high level of abstraction.
So what do you want to do? You want to do Java at the end of the second semester?
I never said that.
You could do that. Well, I mean, you could do that. So now apparently they've put pragmas into Java, which at first blush you say that's kind of ridiculous, because Java is all about information hiding, and pragmas is all about letting the compiler know what the hell you want. But, you know, it sort of breaks the, well, you know, that's my push, is to break the layers between the program and what goes underneath. So I don't know, maybe you do that. Maybe you do Java. Or MATLAB as a language.
No.
You don't like that?
Nah. It's not a language.
C++ seems to be the natural fall on